This is going. Okay, I think we're gone. What we're gonna do today, however, is calculus. It's like, this is legitimate. We're gonna get into basically what it means to be calculus and looking back at what I want to cover and the short day we have. We will see how far we make it. So let's get right into it. We're gonna be talking today about kind of like true calculus. Like, what does calculus really mean? I'm gonna break this down even more. Okay. We've got day 2, AAHL 2. We're gonna go over 5.12. And I'm just gonna call it calculus for now, because for the next 15 minutes we're gonna be talking about calculus and just trying to wrap our head around why does this topic scare people. So first question is gradient, which the poor people call slope. You guys know what gradient is?
Yes.
Okay, sounds good. So if we have a line that looks like this, and we have a point at maybe 5.3, and we have a point at maybe -4, -4. Do you know how to find the gradient of this line?
Yes.
So how do you find it?
y2 minus y1 over x2 minus x1.
Sure. And it really doesn't matter if you put y2 first or if you put x2 first. If you put y2 first or y1 first, you just gotta be consistent. A lot of people like to put y2 first because typically we do positive graphs, so typically the y2 is bigger. So typically it's just like, obviously don't get too stuck on the ones or the twos. The really important thing is that they're kind of stacked up like that. If you choose to put the y first, then the same value x needs to go on one. So let's actually do that. What is the gradient of this line?
700.
So we did 3 minus -4, and then we did 5 minus -4, and we got 7/9. Sweet. Nice job. You guys are gonna do great on the algebra 1 as well. I believe in you guys. So this is gradient, this is slope, this is very easy, kind of boring. And we are able to just say, you know, the statement here. What is the slope of the line? And we're able to answer with the slope is 7/9. The reason we're able to do that is because this is a line. And what do we know about lines and linear graphs?
Their slope stays the same.
Slope stays the same. Slope is always the same. It's just constant slope. That's kind of what makes it a linear line. If we are, trying to identify the slope here, the slope is 7/9, and up here, the slope is still 7/9. 7/9 everywhere. Even if we choose different values, if we choose some other value, some other coordinate here, A, B, we calculate slope, obviously we're gonna still get 7/9. It's all 7/9. So we're going to skip an example out of necessity, and we're gonna go straight to the real deal. Here we are. For today, we're gonna be looking at this graph quite a bit. When we're looking at this graph, we ask the gradient question, right? So we say the same thing. What is the gradient of the line? Well, the first issue is we can't really say line because, you know, colloquially this might be a line, but in math that's not a line, a linear graph. This is a curve. So we're right away gonna have to kind of change up our question a little bit. And the second issue with this question is
Not a constant slope. Yeah.
it's not a constant slope. Exactly. This thing is changing all over the place. So we can't just say like the slope is, let's just say 0, right? 0 is an easy slope. 0 slope, flat across. And I think that the slope is 0 right about here. But it's not going to be 0 much anywhere else, right? Especially at the graph we have drawn, it doesn't really look like it works. So we can't really use this question because it's changing all the time. Before we move on, when I did this thing here, put the line next to the curve, you guys know what that is, what that's called?
Tangent line.
Nice job. Excellent. So we have a tangent line, which is adjacent to our line, or adjacent to our curve, which touches our curve at exactly 1 point. And tangent is kind of a lot of times a barrier between like the kids in calculus who just struggle from the beginning because they just get so scared of that word tangent. Like, oh my God, what is a tangent line? A tangent line is just that line that bumps up against the curve. And so a lot of times we will say the slope of the tangent line, because that's the like easiest way to really conceptualize that slope at a point. So there we go, we have the slope of the tangent line. Glad you guys know tangent, we don't have to talk too much about that. Do you know what the opposite of a tangent line is?
Opposite.
So a tangent line looks like this and kind of goes along with the curve and touches the curve only in one place. The opposite of a tangent line looks like this. And it's perpendicular to the tangent line. And it is called, very strangely, a normal line. Which is like, what, the normal line? Why is it called that? But that is something that will come up. You might have a question that says, what's the what's the slope of the normal line? Which is just the tangent line, perpendicular, opposite reciprocal. So just again, trying to figure out what it is that you guys know, since I wasn't with you guys last year. So, if we want to figure out the slope at a particular point, let's say I want to find the slope, and so I want to use my slope formula, right? I'm going to choose these 2 points, and that's going to make a line that looks like that. But is that a tangent line? No, it is a line, and it will give me a slope, right? I mean, it has 2 points, we can calculate slope, so the slope does exist, but what is it used for? Like, what is the slope that's going to show up? Is it the slope at a point? Is it the slope?
Straight line.
Slope of the line intersecting those points, not really the actual curve.
Right, so this is going to be the average rate of change. So the average rate of change, and already we're starting to get to the point where we're like, adding on these different questions you might hear. It might be about the slope of the tangent line, it might be about the slope of the normal line. It might be about the average rate of change. The average rate of change, again, really is not calculus. This is just take 2 points and calculate an average rate of change. You're gonna get, this does kind of look like decent as far as calculating the slope, but we know it's not gonna be great. You're gonna have some that are a little bit less steep, you're gonna have some that are a little bit more steep, and it's gonna average to the white line. Okay. Now, what happens if we really want to figure out the slope at a particular point? So what if this right here, we'll call this A. What if I really want to know the slope of our graph, and let's start by labeling stuff. What if I really want to know what is the slope of f of x at the value x equals a? Okay. This average rate of change, is that doing a decent job? Is it doing a great job? Definitely not, right? This, curve here looks like its slope is much steeper than our line that I've randomly drawn with this point down here, B. Now, how can we make this a better kind of guess? Is we can slide some of this stuff around. So, if we slide B over here, I don't know if this is gonna work. Let me grab it. And then we kind of change up our question so it looks more like this. Is that a better representation of our slope? It is getting closer. So what we're figuring out is, if we want the average rate of change of a big thing, obviously it's going to be less specific, and as we have the average rate of change of a smaller and smaller region, it's getting more and more accurate to that region, which is true in just about anything. That's definitely not some, hot topic. So, what would we have to do to figure out really the best precise rate of change? Keep shrinking and keep shrinking and keep shrinking that distance between A and B. So, let's just get rid of that. If we keep moving B, and B keeps creeping closer and closer and closer and closer to A, when it's right here, that looks pretty good. But we're eternally picky, right? It could be better. What if B was closer? It could be better. What if B was closer? And we're never quite satisfied. So, average rate of change approach having 1p or 2p? What do we think? I think just one. I don't know. Whatever. Approaches, and here comes a new word, instantaneous. We're just spelling this morning like crazy, aren't we? Instantaneous rate of change. Instantaneous rate of change just meaning the change exactly at the point we're looking for, as B approaches A. So we can use our average rate of change, and the closer B gets, and the closer B gets, the better, the better, the better. We're doing good. Now, here's what we've got as B approaches A. And what does that remind us of?
The limits that we just
The limits that we just covered. And why did we do limits yesterday and we're doing this today? Of course, because we're going to be incorporating limits. So, where do limits enter the scene? All right, here comes the real calculusy stuff. All right, this seems to be something that they can't ever quite decide to name. It seems like every 5 years they want to make the name even more complicated. So as of right now, it seems like the IB program wants to call this limits with first principles. And so we want to build a limit because we want that B to be approaching A, and we want to use our slope stuff that we have. So we're trying to fuse limits with slopes. Okay, so let's start first. How about don't write this down? Let's just craft for a second. What we do know is, y of x, interesting. We do know this, and that is the slope formula. And if we kind of go back to the picture that we had before, A is what we want, B is what's kind of getting closer. So if we erase these, if we erase these 2's and these 1's and we replace them with A's and B's, we can think about the A, that's the one we want, and we can be thinking about taking away the B, that's the one that's kind of getting closer. But again, ideally, that B is sneaking and is like all the way right up against our function. Okay, here's what we're gonna do. We're gonna, don't do that, please come back. Okay, we're going to take that, and here is the limits with first principles, which I think is a simple thing. The limits as h goes to 0 Make sure you write it down correctly, for sure. And then we'll talk about what the heck any of that means. Okay, when you see this, are you seeing jumbled up letters or are you seeing something recognizable? Is there any piece of this that looks somewhat familiar?
X.
F of x, which is just the function, right? That's nice, that's nice and familiar. We do have a weird h in there, and that h is probably like clogging up our brain a little bit and making it feel like there's a lot of crazy stuff going on here. But remember, our goal is to incorporate limits and slopes together. Do you see that slope formula in this jumbled up mess, right? Here's your big fraction, here's your minus, here's your one term, here's your other term. I say term, but I should say coordinate, right? So, on the top, do you have y values? Yes. These are your f of x values, which we know are the same thing as y's. And on the bottom, you have just plain old x values. So now are we seeing the slope formula kind of appear in there? So what the heck is this h stuff, right? Why? We've never seen an h before.
Is it just like the distance between, the x distance between, like in?
Right, so basically, one of these points, let's say that it is, we can call it this one here. This is just x, f of x. You're just x point and your y point. And this point is still using the same function. It still has an f, so it's still on there. This one, it is going to be x plus h and f of x plus h. This point is x plus a little bit extra, right? And I suppose these are backwards because if they were adding an x, then maybe maybe h is a negative number for now, I don't know. Probably should switch these around, but it's okay. That h, just like you were saying, is that little distance that's between these 2 points. And here's why we like the limits, because those limits are allowing us to shrink that h to be 0. So our goal is try to solve this, try to figure this out. That h keeps shrinking, our dot keeps approaching, sneaking closer and closer and closer. And eventually, if h does get to be 0, boop, we've done it. But it's also kind of a weird process, because how can you do the slope between 2 points that are the same point? It's just gonna give you 0. So, here's what we're gonna do. Now we can. Okay. The denominator of this big ugly limit. What's going on in the denominator down there? X plus h minus x. Of course, right? We don't need this x nonsense, right? X plus h, okay, that makes sense. And subtracting the other x, okay, that makes sense. But the plus x minus x are opposites, they're eliminating each other. And so h is the only thing left on the bottom. And so this truly is the limits with first principles. The plus x plus h minus x, you will never see again. You only get to see it the very first time you introduce it. I'm sure there are some teachers who would just slap you this and show you how to do it, but especially in HO, I think it's definitely worth it so that this isn't just random stuff. This is the slope formula, and we're really hoping that that h is gonna approach 0, that distance between is gonna approach 0. Now, we talked about limits. Limits are great because if you have a nice boring function, you can just take that number, plug it in, and get the answer. What's our issue going on here? If we plug in 0 for h, we have a 0 denominator, and you cannot do that. So, the nice thing about limits is it allows you to kind of pause that, try to make it work, and hopefully you can massage that problem and kind of just get rid of that h, and we'll be okay. So, let's do a little question here. Okay. Instant change is ready to change. Sweet. Alright. We're finally here. Find the instantaneous rate of change of 5x plus 1 of x at x equals 12. Okay, first of all, rate this question's difficulty from 1 to 1,000,000. 1. Why is this so easy? It's a line, it's a linear line, and it has a constant gradient, a constant slope. What's the answer gonna be? 5. So, I understand that this is starting very basic, but let's just throw this into the limits first principle, kind of see how it works. So we know that our x is gonna be 12. So we could work with the limit as h goes to 0 of f of 12 plus h minus f of 12 over h. So now we're going to use this f and kind of plug that in over here. This is where it gets a little bit messy because we need to make sure we're substituting correctly where the 12 goes into the x. That's not very hard, but this part where the 12 plus h has to go into the x. So just make sure you're kind of substituting correctly, and this will be an easy. Okay. The limit as h goes to 0, plug it in. The first one, we want to substitute 12 plus h. 5, 12 plus h plus 1. Everybody cool with that? The other part's very easy. Minus f of 12, which is going to be 5 minus 1 over h. Now, teacher moment, maybe more so because I haven't been teaching IB for years. I feel like I have to point this out. We have a minus the second f of x, which means all of this stuff needs to be minused, which means, distribute that negative or however you want to say it. That is, as much calculus as we're doing, that algebra 1 distributing is what is going to, at least in years past, teaching regular calculus or AP calculus, that ends up being the killer. So let's simplify all that down. We have the limit as h goes to 0 of 60 plus 5h plus 1 minus 60 minus 1. So it's, is that a plus 1? It's a plus 1 minus plus 1. So it's a minus 1 all over h. And what are we noticing now?
You combine all terms.
Right, combine like terms. We have a positive 60, we have a minus 60. We have a positive 1, we have a minus 1. And now, those h's cancel out. And what's the answer going to be? Now, we knew that before this question even started. But it's worth starting really simple, seeing how this process works. Plug this stuff in, do your distributing, make sure that negative sign gets handled, and you are looking for basically everything except for h's. Same, they're all gonna be crossing out. And if you're doing this question and something doesn't cross out, you're wrong. Pause, and go back and figure it out. A lot of times, I see students, they have a plus 1 here, and they have a plus 1 here, because they forgot to do the distribute negative, and it's like, low key, how can you mess that up? Because obviously we know these should be opposites, and they're not. So, we got it. Now, let's go do a question that actually deserves our time, and we can't solve it in 30 seconds. Okay, find instantaneous rate of change. I would write this out if we didn't have a pep rally today, so you got lucky. All right, g of x at x equals 3, x equals 10, and x equals negative 1. G of x equals x squared minus 6. Okay, we have a function, x squared minus 6. This function, is it linear? No. How's the slope looking? It's changing all the time. So, at these 3 different values, we can expect 3 different slopes. That means we can't just find the first one and say it's good for all of them. We're gonna have to calculate all 3 of them. So, let's do this question. I'm gonna go relatively quickly because I feel like we're doing great here. The limit as h goes to 0 of the first piece is gonna be g of x plus h. And we're gonna subtract g of x. The first number we want is 3, and of course we have g right there. Make sure you plug in the x plus h into the x. That is like where we're gonna get stuck. So the limit as x we've got plugging in x plus h, you know x is gonna be 3. 3 plus h squared minus 6, and then we're gonna subtract 3 squared minus 6. Make sure, I like to use these brackets. Honestly, I like to use the brackets just because they remind me to like, please don't mess up that negative sign, please. So, before we go on, did we set it up right? We started with g of x squared minus 6, x squared minus 6. We plugged in x plus h, 3 plus h. Then we got to the other side. We used g, x squared minus 6, and we plugged in just the 3. No h on that side. Hopefully now, we're gonna do a little bit of simplifying. We're gonna have some positive numbers, some negative numbers. They're gonna cancel out. This time it's not so easy though. We have parentheses squared. Well, what are we gonna do with that? FOIL, of course, and it's 3 plus h. H is acting like our variable, so we're gonna get a nice traditional kind of quadratic. Just do a little here. Limit as h goes to 0. Give myself a nice long fraction. The FOIL would be 9. Then we're gonna have 3h, 3h, which is gonna make 6h. And then we're gonna have h squared. That's the FOIL. We're good with that? We're gonna have minus 6. We're gonna have minus, and that stuff is all numbers, so that's gonna be easy. 3 squared is 9, and that's gonna be a negative 9. We're gonna have negative 6, but that's gonna be a negative negative 6, so that's gonna be plus 6. And hopefully we have a nice balance. Anything that we have that's a positive, we found a negative for. So this 9, do we have the opposite of the 9?
Yeah.
Yes. This one has an h, it's probably gonna have to stay. This one has h squared, it's probably gonna have to stay. This one is a negative 6, do we have a positive 6?
Yes.
Yes. All right, and we're doing pretty good here. We need to now get rid of that h, and we'll be all right. So, how do we simplify that to get rid of that h? Well, we just need to take one h from both of those different pieces. If you want to think about it like, you know, starting here, doing a GCF. And pulling out that h. And, you know, if you want to think about it like that, sure, but we're just taking one h, one h, one h from all of it. I think you guys got that. So, now we have the limit as h goes to 0, but we've gotten rid of that h on the bottom, 6 plus h. And so, if we plug in a 0, we're safe now. Even though we still have an h, it's not a divide by h, so we're okay. All right, what is the instantaneous rate of change at the x value of 3? 6. Okay, now, that's not the most fun problem in the whole world, to be honest. In fact, I don't really like doing it very much. This question said, I want to find the slope at 3. Okay, cool. It's 6. But it also said, and 10, and negative 1. And you know what? God, really? do I have to do that for sure? I gotta figure out something else. So, we could kind of start over, do the whole thing again. But maybe you're already ahead of me. What we've been doing is we have been starting by plugging in those 3s because we knew we were looking for that 3. But if we think bigger picture, if we can leave the x in there. We can get a function with x's and h's, which is more difficult because we got two variables. But if we get to the end and we have x's and h's, the h's go away, then we can use that to plug in any number we want. So it's almost like instead of going specifically for the 3 right now, let's go a little bit harder. We can get the generic answer, and then we can just boom, 10, boom, 3, boom, -1. So let's do that. Let's do this same question again. G of x equals x squared minus 6. This time, instead of right away plugging in 3, let's leave all the numbers out and let's go for like a letters only challenge. So, the limit as h goes to 0 with an h on the bottom. We've got g of x plus h, and there's our g. We've already done this once, but we're gonna leave the x's in there. X plus h squared minus 6. Everybody cool with that? Which is the same thing, we just left the x, and then we're gonna be minusing, and this is really easy because it's just the same thing. Leave the x squared minus 6. So if we don't work on this, h goes to 0. Again, this other part is very easy, minus x squared plus 6. But this first part, we're gonna have to do some foiling with two variables. But it ain't really all that hard. It's gonna be x squared, xh, and we're gonna have 2 of those, plus 2xh, and then we're gonna have h squared, and then we still have that minus 6, don't forget. Okay. Pause for a second. Can we all get that far? Again, it's funky because we have to do foiling with 2 variables, but we're IB kids, we can handle that. At this point, hopefully we have that stuff that's canceling out. We got stuff that's canceling out?
Yes.
I know we have the 6 and the minus 6. Anything else?
X squared.
Right, also we have the x squared, the negative x squared. And so now we're here, and nothing's canceling out. We have only terms left that have the h, and this looks very familiar again because we've already done this question. We know that